we have already run out of IPv4 addresses. There's basically a shuffle going on for those IPv4 addresses that are recycled. You know, organizations drop off, like companies go out of business, or organizations, you know, shutter themselves. They might have had IPv4 addresses. They get reclaimed. Maybe our push to the cloud puts things up there, and we don't need as many public IP addresses. We still need public IP addresses in cloud distributions, by the way. Don't hear me and jump to that conclusion. So the structure of IPv6 addresses is an interesting one. And the first thing that I want you to understand is all your operating systems support this, or are a few button clicks to support it. Most operating systems are what we call dual stack. First thing I want you to take away, dual stack. Just the reality. We used to, you know, talk about earlier versions of Windows that could be run as dual stack and older versions that couldn't. Most operating systems can run. Now, whether your firewalls run IPv6, whether your routing and multi-layer switches run IPv6, that's a beast of a different flavor, okay? Now, what's interesting is there are all these really special automatic kind of tunnels that are set up in IPv6. So it's really weird that you can actually communicate IPv6 over an IPv4 network. And one of the reasons why you're going to find your workstations have IPv6 addresses is because of some of the automatic tunnels that are set up. We don't get into that. But what I do want you to realize is, yeah, IPv4 or IPv6 and IPv4 can run at the same time. That's what to expect. And you're generally not going to be turning off IPv4 if you run IPv6. That would be weird, okay? You'd have to have a really narrow use case to turn off IPv4. So if you're running IPv6, you're probably running dual stack. And there's ways that you're going to dynamically get addresses. And the addresses are written very differently. This is the first thing that's going to kind of make this a less appealing protocol, is the addresses are really long. Okay? They're long because this is 128 bits. 128 bits is 4 times the number of bits that we can have in IPv4. And there's lots of different, you know, ways that people say how many of these you have. Like stars in, you know, all the galaxies and grains of sand. We get a lot of these, okay? I'm not going to focus on the fact that we get a lot. You get a lot. More than you need, okay? And I really mean more than you need. So there's no longer a scarcity of this, okay? We have an abundance of these. And we're being very careful about how we roll this protocol out so that 100 years in the future, we don't start second-guess choices that we made with this protocol. Now, they're written in hexadecimal, like MAC addresses. MAC addresses are written in hexadecimal, so we're going to see numbers, but also letters going up to letter F. And they're separated. Now, in this case, we are consistent. We're always going to use colons for the separation. Always. With MAC addresses, we had periods and hyphens and colons. And nope, always a colon. And we saw something interesting when I did an NS lookup earlier today. Let me see if I can dig that back up. When I did the command ns lookup on Yahoo, I got an interesting result. Well, that bake, I'll go back. I got an interesting result that was exposure of this thing right here, which is the shortening of the addresses. If it's 128 bits long, that means, and each hexadecimal digit represents 4 bits. I need 32 digits with an extra 6 colons. Is it 6? 1, 2, 3, 4, 5, 6, 7. 7 colons. 32 characters plus another 7 for separators. That's kind of messy. It's like 41 characters to write an address. Way worse than IPv4, just in terms of bulk of our humanity, okay? Oh, Bo, let's actually see that. I really appreciate Bo telling us Facebook's address. Cool. Okay, so I think we got that baked. I didn't know that, by the way. Did not know that. So we're going to do a CMD. And I'll do NS lookup for Yahoo. And we can see our addresses. Now, Yahoo people, I mean, they're just scraping by. They're really good. Oops, you can't see me right now. You can't see me. Okay. Our addresses, 2001. Now, these are global addresses. The 2001 space is it's not the extent of global addresses, but that basically is, hey, this is a public address. This is equivalent of public. And they have done what is called shortening. And what I want you to see is that they're only going to put in non-zero values. If it's a 0, they drop it off. And if there's a lot of zeros in multiple 1 or more octets, which is a group of 4 characters, they put in a double colon. Now, you don't need to know how to read this. You don't need to know how to shorten an address. I'm going to go over the rule just because it's helpful if you go deeper, and it's never a bad thing to see a little bit more. But here's the way that I look at it. You can see they are allocated. This portion is the subnet ID. The first 64 bits is the subnet ID. They were allocated. Yahoo was allocated 2001 499844. That's what they were allocated. And they actually do subnetting in the 4th octet. We're going to see this in the address structure. What's cool is if you're assigned a site ID, which is the first 48 bits, that gives you the ability for 65,536 subnets. So you're granted the minimum site that you would get gives you 65,000 and change subnets. Really nice. That's enough for your whole organization. You're probably going to want to have a few because you have different locations. It's nice to geographically separate them with different sites. So Yahoo actually has a few. They've got 44 and 24 for different site IDs. And then I want you to see these double colons. And thanks for that, Bo. I'm going to, I'm not a Facebook person. So let's see if this is, I'm in uncharted territory. Oh, I see face there. That's cool. It's not a, oh yeah, Facebook. Okay, I see it. I see it. Very cool. Thank you for that, Bo. I wonder if anybody else has fun with it. Google is a G, can't be in hexadecimal, so they don't have those options. Jeez, you know? Mark Zuckerberg must have been really forward-thinking when he created Facebook, thinking that most of that could be represented in hexadecimal in leet speak terminology. Cool. Nice little aside we had there. So in deeper examinations that are focused on IPv6, what we will train you is this. you can drop off leading zeros in what are called quartets. A quartet being a grouping of 4 hexadecimal characters. One thing that's a little interesting is that is an unofficial term. At least it was when we in the industry started using it about 20 years ago. So you can drop off leading zeros. You drop off your leading zeros. And if you have a big group of multiple quartets, you can represent them once and only once with a double colon. And so don't get, the reason why I'm saying this is just don't get caught off guard. If it doesn't look like it's long enough, it's because you can drop off zeros. Now, one of the things that people don't teach you is, and I've seen this in textbooks that cover IPv6, is they don't really tell you what the actual mask that you're typically going to employ. In IPv4, we use all sorts of masks, like /24, /29, /28, /27. Very, very common. In IPv6, one mask to rule them all, /64, chopping the address exactly in half. Do not break this. People are not nearly clear enough, and a lot of times they're not clear because they don't know it. It's /64. That's the mask you're going to use. If you do anything different, you are in the weeds, and you are on your own, okay? Now, one of the things that's really interesting is they rethought a lot of the mechanisms for communication. Here are the mechanisms of communication for IPv6, and I want you to tell me which is new and which one is missing. Unicast, multicast, anycast. Which one is new? Which one is missing? Like, as in, are we seeing something here that we haven't seen before? And if we're talking about different communication, are there communication types that exist but not in IPv6? Okay, so anycast is new, broadcast is missing, okay? Anycast is actually a really good mechanism, and believe it or not, you can make it work in IPv4. Networking people, the ones who do really funky stuff, yeah, anycast absolutely can be made to work in IPv4. Here's what it is. 1 to nearest. I want you to think about services and getting things like time. Let's say you're getting time on IPv6. It's okay to get your time from the nearest server. What about, there are these things called content delivery networks, which prop up resources. Let's say they're videos. We put our videos for this course in a CDN. They're propagated to a bunch of different data centers so that people, when they get it, they're going to get it from a data center that is the nearest one to them. Anycast is actually accomplished via routing. What actually happens is we advertise that address. Any router can advertise that address if it has connectivity, and we can have lots of different routers say, "Hey, I have reachability to this." And then dynamic routing protocols are really good at path selection, so they're going to choose the best way to get to your address. That's anycast. This is more or less like, hey, you can't cover IPv6 if you don't cover the basics. And these are the basics. Multicast is much more baked in for IPv6. Multicast is used pretty sparingly in IPv4, but in IPv6, it's a fundamental communication, and it takes the place of broadcast. So you get broadcast kind of capabilities in multicast if you want, but it's a lot more elegant. And you could do any kind of elegant communication to a group. There's groups for protocol or devices that are running a protocol. There's groups for your routers. There's groups for all systems. So if you do need to communicate with everybody, there's ways of doing it. It's just not formally called a broadcast, okay? And then unicast. When we communicate with Facebook's address or Yahoo's address, that's the global unicast address, typically starting with 2001, which I believe is the first year that we started allocating actual global addresses, 2001. Then there's link local and unique local. Link local is an awesome, if you work with IPv6, this is the thing that is the game changer. This is equivalent to a PIPA, the automatic private IP. Do you remember the address for a PIPA? Somebody does probably. Chat that in. We're going to see this. And then unique local, which is the equivalent of private addresses. We tried to not do private addresses for IPv6. That didn't last very long. So there is the construct of private. 169.254. Great. A PIPA is 169.254. And we're going to see that link local starts off with FE80. Okay. Okay. Bah. We've got crazy stuff on the screen. For those of you test takers, this is not as a page to study. So this is more real world and, hey, we're trying to enrich ourselves with respect to IPv6. Global unicast addresses, these are the equivalent of public. They're routable on the internet. Like link local can't be routable, okay? They start off with 2000 something. Notice they use prefix notation here. And here's actually how it works. So people that are out there going, this stuff is so foreign to me. This is a really intimidating protocol. Here's the first place where you're going to be like, oh, that's kind of cool. You might not feel that way today, but you might feel it the second or third time you see it. Like if you go through CCNA, you'll see this. The site prefix is what is allocated to a site, as in your headquarters, or maybe you've got a data center. That's going to get a /48. That's going to get a /48. Now you go, what does that mean to me? What that means is you don't actually deploy a /48. What you do is you deploy a /64. So this space right here in 16 bits between /48, /64, that's your place to subnet. That is your playground. In a 16-bit space, you can have 65,536. So you can have 65,000 subnets, and you get to do fun stuff here, okay? So that's your subnet ID. And then on the right-hand side is your unique identifier. That is known as the interface ID. In IPv4, we call it the host portion. In IPv6, the full technical name is interface ID. I still think of it as the host portion. Sometimes I'll say it's the host portion for IPv6, but the technical term is interface ID. What's cool is we're actually seeing how it is working here. We just taught you, well, I mean, maybe it's a stretch that we taught you subnetting, but this page is subnetting. This is the whole page on subnetting in the real world of how you'd get an IPv6 address and then start to deploy it. Just count in that 16-bit space there and go around. And a lot of your links between devices, by the way, don't even need a public subnet. They can get by with link local addresses. One of the address types that we aren't going to worry about, this is in purely for posterity's sake, is what is called unique local. For a few years, and I can't remember how many years, we were like, we're not going to have private addresses for IPv6. And we had them, and then we lost them, and then we had them again. So there are battles that that are taking place even still probably to this day on how IPv6 is going to work. But it's nice to be able to use the same idea as a private address. So you could start with FC and you could address your environment and you could build your own IPv6 network. I don't know anybody who does this. It's not important for network operation in anything we teach, but hey, it's out there and it helps us realize that there are similarities between IPv4 and IPv6. For anybody who really has to work with IPv6 in their future, if you're going to go deeper into networking, this address is actually gold. This address is really an important one. And I've switched over to a slide titled Link Local. Link Local Unicast. All the fundamental communication that takes place in IPv6 is generally done with link local. Okay? Communication for the equivalent of ARP is link local. Addressing the equivalent of DHCP, and there is a version of DHCP that's link local. So what this is it's a means of addressing ourselves. It's a means of addressing ourselves and communicating with other stations on the subnet. Now, remember when I asked you what the APIPA address was? What is the purpose of APIPA, Automatic Private IP Assignment? It was that 169.254 address. That address is to communicate with other devices on the subnet. The unfortunate thing is nobody cared, nobody used it, so it's just like literally this residue of the intention of supporting it without anybody actually using it. This thing is used. It's used for all of the fundamental communication. If you're not routing, you're probably doing this. So you're going to see it used by dynamic routing protocols and the fundamental communication that helps us get our traffic from one place to another. This is generally just plugged in. We start off with FE80, and then we address ourselves. And if you have IPv6 on for your workstation, you are probably running that address. You're going to see it a lot. So you're going to do a good job assigning yourself a link local address. That's done automatically. It's done automatically. Let me just show you here. Stuff really does work the way that we're explaining it. I've got a dual stack device. It got one of these link local addresses. I'm not doing anything with IPv6, but it baked it in because there's different kind of tunnel mechanisms that Windows likes to build. And I think the kind of tunnel that IPv6 uses on Windows is like called a Teredo tunnel. And it's an automatic kind of tunnel that is configured for communication. So, not unusual to self-assign one of these. Not unusual to self-assign an address. It isn't a bad idea to recognize that the public space uses 2001 and that the link local is FE80. Here we have unique local, kind of just there for posterity, okay? 2001 for public IPv6. and FE80 for link local.